Hello friends, welcome to follow-up. In this video and a follow-up video, we're going to look at a strategy called search range shrinkage, which can be regarded as one ingredient in general binary search algorithm or binary search idea. So in this video, we're going to look at problem 162, find peak element. This is also a daily challenge problem. So our plan will be the following. First, we're going to digest the requirements, and then we look at the coding. And in between, we're going to explain the thought process and the algorithm. So here, a peak element is an element that is strictly greater than its neighbors. Notice that it does not specify the number of neighbors, right? As long as we have something like this. So this will be a peak. So given a zero index integer array called nums, we want to find a peak element and return the index. If the array contains multiple peaks, return the index to any of the peaks, right? So also we regard that to the first element and to the left of the first element and to the right of the last element, there will be some imagined element has value negative infinity, right? So we want to write an algorithm that runs in logarithm time complexity, right, up to a constant. So that's the big O notation, right? So actually this requirement is very suggestive. Basically, we can consider binary search, right? So here we have two examples. In the first example, we have a peak at element 3, right? Because 3 is greater than 2 and greater than 1. And in the second one, we have 2 can be a peak, and this 6 can be another one, right? We can return index 1, and we can return index 5, right? Both are okay. So here, the length of this list is bounded above by 1000, and the elements in the list are 32-bit signed integers, right? So, and also the adjacent elements are different. So with that said, we are ready to look at the algorithm and the coding. So here, the main condition is that we want to find an index I such that this index, let's call this nums list A, right? AI is greater than the left and also greater than the right strictly, right? So for this problem, if we want to solve it, we can use a for loop. This is ON time complexity. That's sort of trivial, right? And then here the main thing is how do we do search range shrinkage. So first, I'm going to organize this coding like the following. We'll first treat several edge cases, and then we look at the general search range shrinkage. First, I'm going to get the length of this A, just for convenience of writing. So if n equals 1, so here we start from n equals 1. The reason is that the length is bounded below by 1. So if this is the case, it's already a peak because it's larger than the two negative infinities in both sides. So we are going to return the index 0. And then we also need to consider the two edge cases if length n is greater than 1. So to the very left and to the very right. So for the left ends, so we can see if A0 is greater than A1, right? Because we can regard the index left has a negative infinity. So the other equality is already satisfied. So in this case, we are going to return index 0. So symmetrically, we can consider A n minus 1. So if it's greater than A n minus 2, right? Then we just need to return n minus 1. So this is another end, right? So these are some edge cases. So this is just for safety, right, in some sense. So next, we treat the general case. So here we want to use search range shrinkage. This is actually very like binary search. So here we can initialize low and high, which is 1 and n minus 1, because we have already considered 0. You can start at n minus 2 if you like. So here, well, low is less than high. So we can do search range shrinkage using this pattern, low. So let's shrink by half, high minus low, integer division by 2, right? Then the main condition will be the following. If a mid is greater than a mid minus 1, and a mid is greater than the right, that is mid plus 1. So in this situation, we already found one peak, right? We can return this mid. Otherwise, so we are going to lie in the complementary of this condition. So either a is less than or equal to a mid minus 1. But in this problem, neighboring element will be different. Then we will have a mid strictly less than this left, or a mid strictly less than the right, right? So let's consider this one. If a mid is strictly less than a mid minus 1. In this case, a mid minus 1 is very large, right? So in this case, we can set high equals mid. Then we can search, right? So you can you can consider a picture in your mind, right? So mid is less than mid minus 1. So you can think. So here is mid minus 1. So it has a very large value, right? Large value. And then we have mid, because mid is in the left. So we have a smaller value. So, the peak will be in the left of mid, right? So we set high equals mid. So another case is that a mid is strictly less than a mid plus 1. So in this case, we know that, let's see, we have mid. It has a smaller value, right? Then we have mid plus 1. So that has a larger value. So we know that the peak, there must be one peak to the right of mid. So we can set low equals mid. Yeah, actually for this problem, due to the assumption, there must be a peak so we just need to leave this as it is. So otherwise, you can return low, because low as always make this, or you can return high. For this problem, that's not it's not that essential. You can even comment that out. So now let's do a test. Yeah, it passes the first example. Now let's look at the generic case. Yeah, I guess one problem for this problem is that what if there's no peak, right? But due to the assumption that we imagine the two negative infinities in both ends, there must be a peak. That's why we can just leave the code as this. There must be some return, right? So with that said, I guess that's basically about it for this problem. I guess for this problem, the major point is that you realize this condition, right? Realize this condition, and then you can do shrinkage. So here, each time we do a roughly half of the search range, right? So therefore, the time complexity will be logarithm the length of the search space, search range, right? The absolute value here I wrote is roughly O of n, right? So you can see here is n minus 1 plus 1, right? N minus 1 is at n, right? So with that said, that's about it for this problem. So you are welcome to follow up for problem 852. Thank you.